We are now going to start the second lecture in our series on earthquakes. We'll call this one Earthquakes number 2. This is chapter 9 in our textbook. Now, one thing I want to pick up on from last time was I was defining parts of a fault. So here's now a textbook sketch of a fault, and we've got the scarp, which is the surface expression. We've got the hanging wall and the footwall. And I showed those last time, but I didn't define them for you, okay? Footwall and hanging wall. And they help us describe the geometry of a fault. And what I like about this picture from a textbook is that there's a picture of a miner in a tunnel. And that's where this name came from. Where essentially, if you have a fault and you draw a stick figure across that fault, the foot block, let's call it the footwall is down here where the feet of the guy would be, and the hanging wall block is up where his head is, and that's where you would hang a lantern. So it was where the hanging wall would be. And we're going to use those terms in order to define different types of faults based on if the hanging wall goes up or the footwall goes up. And in our notes today, we're specifically going through not 3 dot, but 3 types of faults. Ooh, that's bad penmanship. All right, we've got 3 types of faults to cover today, and they're going to be defined in 2 ways. They're going to be defined by the relative movement directions of the 2 blocks, hanging wall up or hanging wall down. They're also going to be defined by the angle of the fault plane. These are the 2 things that a structural geologist would care about as they're assessing a fault. So let's just go ahead and dive right in. The first type of fault to talk about is called a normal fault. And I think these are called normal faults because miners considered them the most regular. And what we see in a normal fault, we'll go ahead and draw one down here, is, so here's the normal fault, there's our fault, here are our 2 blocks. And what we see on a normal fault is this side goes down relative to this side. The tectonic reason for this is divergence and its extension, which elongates a space. And the way to describe this with hanging wall is we would say that for a normal fault, the hanging wall goes down. And I'm not going to practice this with you every single time, but draw your little stick figure. And notice how the side with this head on is going down. So that makes it a normal fault. Tectonically, this is extension. And this is stretching. Let's also go ahead and just throw divergence in as well. These are all the terms I want you to be associating with normal fault. They tend to be fairly shallow in the crust in terms of like where would we expect to see them. They tend to be shallow. And it's occurring in these rift basins produced by divergence. Sometimes we get pairs of normal faults or groups of normal faults occurring together. And sometimes these will create grabens. And graben is a word for a rift. Like the East Africa Rift Valley, you can get a situation where because of extension, there's actually like a bit of land that has fallen down. And if you look, notice that both sides are normal faults. If you were to draw in the stick figure, you would see that in both cases, the let's see, did I draw that right? Yeah, the hanging wall is going down. I'll throw in a picture of a normal fault, and then we can progress to the next type. In fact, let's scroll down, make this nice and big for all the eyeballs to see. So, and let's go blue. And so the way to find, here's a cool picture of a normal fault. There's the fault plane. We find it by finding like layers. And so this red unit is equivalent to this red unit, and we can see how this side has dropped down relative to this side up. There's our normal fault. We are extending the paper in these directions. We can do the same thing over on this side. You can find all the cracks, find a like rock unit within this outcrop. It's harder to see, but draw your eye to this unit and find where that unit exists to the right. A piece of it exists here, and more of it exists here. So we have a fault here, we have a fault here, and this side is going down, this side relatively is going up. We draw in our hanging wall guy. Here's our hanging wall, and let's make sure we see it. The head wall, where it's headed is going down, so that's a normal fault. That's something to practice if you're not seeing it as we're going right now. All right, the second type of fault is the exact opposite kind of fault, and in fact, it has a name that kind of means opposite. It is called a reverse fault, and a reverse fault occurs due to compression and shortening. Plate tectonics, this is convergence, this is subduction zones, and continent collisions making mountains. In terms of our hanging wall, this is the hanging wall goes up. To draw that with you, we could do, here's our surface, there's our fault, and here's our other surface. And so we have this side going up, this side going down. The motion on here, well, I guess we could draw our guy. There's our stick figure, and notice how the head side is going up. And if we drew our tectonic arrows, it is colliding lithosphere together to produce this kind of fault. Let's go ahead and throw in the word mountain building. And now a picture. Let's see, what do we have to choose from here? Here's a pretty good picture. It's large scale, just like in the previous pictures. Let's find the fault and let's find like units. And so here is our fault sliding through the picture, and this white unit is correlative with this white unit, and so we can see that this side is going up and that side is going down. Our plate tectonic pressure is here and here. Now there is a 2A that I would like to briefly introduce to you, or 2 asterisks. It's going to be called a thrust fault, and it's a special kind of reverse fault where the angle of the fault is low, like 10 to 15 degrees. It's a really shallow, let's say, reverse fault. And these are really important in mountain building. So we're going to say important for mountains. I'll show you a cartoon of one of these thrust faults here in action. We'll see what you think about it. But the idea for building a mountain range is like step by step. You have these, the blue arrows are showing this tectonic convergence. There is a break here, shown by the red line, but then notice that when the break occurs, this whole big unit here kind of like oozes and slides up on top, and it creates a fault that actually has a very low angle. It repeats the section. Notice how B is already on top of B. That's because of the fault motion, and then it has built these mountains. Anyways, that's a special type of thrust fault. All right, the third type of fault to consider today is a strike-slip fault. And these are our shear faults. Strike-slip faults. They are associated with horizontal motion. It's not up or down. Horizontal motion. They're produced by shear. And so my sketch that I'm going to make with you right now is a little bit different. We're going to imagine we're a bird, and we're looking down on a system. There's our fault, and we have a river that's flowing on one side of the fault, and then we see the river now again here. This can actually be produced by a strike-slip fault if the motion on the fault is this side in this direction and this side in this direction. We call these, we name these faults more specifically based on their direction. So I'm going to put the word direction here. Okay, because if you have a strike-slip fault, which way is it moving? Is it moving to the left or to the right? And so we actually have 2 different types of strike-slip faults. One is called a right lateral strike-slip fault, and another is called a left lateral strike slip fault. And so let's just look at this one example, and hopefully this helps you. Let's imagine you're standing right here. Oh, that's a happy face. Anyways, you're standing right here and you're looking in this direction. You look across the fault and you see which way the other side of the fault moved. Well, in this case, as we look across the fault, we notice that the river has moved to the left, so that this example is a left lateral strike slip fault. It's pretty neat because they have this extra information associated with them. And maybe what we should put a little bit in here is like, you stand on one side and check the direction of the other. Let's actually say that. Let's say check direction of other side of fault. Let me show you a really cool example of a strike slip fault. I'm going to show you two. These can be pretty photogenic and some of them are famous. This is an example of the San Andreas Fault. We're looking across it from kind of a bird's eye view with the topography shown on a DEM. And so let's decide what type of fault this is. If we are standing right here at the red dot and we look across the fault, which way has it moved? Well, I'm going to suggest to you that here's our fault. The top is moving to the right, the bottom is moving to the left in this picture. And the reason I can tell is we have this creek, and the creek gets offset. So if we were standing in the creek here, we see that the creek picks up to the right. We can do that with all these drainages. And that's one of the coolest things about the San Andreas. Another fault occurred in 2023 in Turkey. It caused a lot of death and destruction, right? It was a very sad event. And as people went out to photograph it, they came up with some really amazing images. And here's a great example of a road in a farmer's field. And we can draw in where the fault is, right? Now, what kind of fault is this? We could pause it. I'm going to tell you the answer. Because if I'm standing here, where'd the road go? The road went to the left. And so this one is a left lateral strike slip fault.